Welcome back. Today we're going to talk about sample means, and I've already got a statement started up here. But when we're talking about sample means, this is the most common statistic used in quantitative data, because essentially what we're doing is we're taking every possible sample and finding the mean of it, and then we're creating a distribution from those means from the sample. Okay, so it's the distribution of all the values taken by the sample mean, mean, and that's x bar in all possible samples of the same size. So we take all possible samples of the same size, we find the mean, and we say, how are those means distributed, and how does it compare to the mean of the overall population? So that's what we're doing here. So when we talked about proportions, sample proportions, that's more of a categorical variable, right? So we're talking about, for example, what proportion of U.S. adults has watched Survivor, or what percent of the population attended church last week. We're concerned about a proportion representative of the population, something they're doing, or something they know, or something categorical that we can measure. Did they or did they not? What is the percent of that? With sample means, we're talking about quantitative data. We're talking about heights. We're talking about different things that can be measured, and then finding the mean of it based on a certain size group. So as we look at this, the important ideas that come out of this are the sampling distribution, of x bar, meaning these. So this is like, remember, sample mean. So x bar is the sample mean. So the sampling distribution of all possible means taken from all possible samples. And like our sample proportion, it should match. So the mean of our sampling distribution, should match the mean of our population. Likewise, so what we can find is something representative of the standard deviation of our sample means, and it's going to be equal to taking the standard deviation and dividing it by the square root of the number of things that we've taken as a sample. And like much of this chapter, what we're concerning ourselves with is this normal? Because if it can be considered normal, we can use all kinds of calculators, right? We can find use that table A. We can find the probability by finding the area underneath. So we're going to ask ourselves if it's approximately normal. So if a population is approximately normal, then the sampling distribution of x bar will also be approximately normal. And what's awesome about that is we can go ahead and set right to work, right? So we can use all of those tools that we can use with an approximately normal setting if we know that the population is approximately normal. So our z-score would look like this, right? So it would be our statistic minus our parameter, and we're going to put that over our standard deviation, correct? So that's how we're going to find this, right? So when we draw in our approximately normal curve, we're going to set it up like this, and we're going to have the mean of our sampling distribution, and then we're going to put on the side here, we're going to put our standard deviation divided by the square root of n. So that's going to be the standard deviation of our sample mean. Okay, so what can we do with this? Well, obviously, what we want to do is we want to say that the sampling distribution of this of the means for this particular sample, this particular piece of quantitative data is normal. And to do that, if the population is normal, then we can start to make some statements about our sampling distribution. So, if the length of a human pregnancy from conception to birth varies according to a distribution that's approximately normal. This is actually really good for us because they tell us that it's approximately normal. So we find out that our mean is 266 days and the standard deviation is 16 days. So we're going to find some probabilities. So what are some questions that might be asked in a situation like this? What is the probability that a person goes more than this number of days or less than this number of days? So the probability that a randomly chosen pregnant woman has a pregnancy that lasts for more than 270 days. So let's think about that for a second. I'm going to draw myself a picture here. 260 goes in the middle here. And what we're calculating is the probability that it would go more than 270 days. So check this out. As you remember from chapter 6, that's represented by this area under this portion of the curve. And so when we look at this value, we have 266, which is our mean, and then we've got 16, which is our standard deviation. We can do it one of two ways, right? We could take our z-score. We could do 270 minus 266. Divide that by our standard deviation, which is 16, right? 270 minus 266 over 16 is equal to 0.25. We could go to our, table A, and we could get that this is equal to 40.13%. Or remember, we can do our normal CDF. And we could go from 270, so wait, hold on, min, and then our max, you put in something like 1,000, right? Or infinity if you've got that, if you've got that functionality in your calculator. We put in our sample mean, which is 266, label this, and we can label our standard deviation of 16. And we get 0.4013, right? So we get the same thing, but I'm showing you how to do it with table A and also with your calculator. So what we've just done now is we've said we've tied together the sampling distribution with the actual piece of data. And so what we can say is we are going to choose an SRS of 6 pregnant women, and we're going to let the mean pregnancy length, we're going to find the mean pregnancy length for the sample. So what does the mean? Well, that's the beauty of this, right? So because the population is approximately normal, this one is approximately normal, which means that x bar is equal to the true mean. And so they're both equal to, the mean of the sampling distribution, I need to relabel that, is equal to the mean, which is 266. I'm not talking about the sample mean. I'm talking about the mean of the sampling distribution, right? It's equal to the population mean of 266. So calculate and interpret the standard deviation of the sampling distribution of x bar. This is a question related to that formula that we have up top. But we need to verify that 10% condition is met. We'll think about it for a second. We have a simple random sample of 6 women. Is 6 women less than 10% of all pregnant women? Yes. Right? There's no question here. We are definitely the 10% condition. Yes. Check. And so what we can do is we can say now that we can use our formula up top. And so our standard deviation of our sample mean is equal to standard deviation over the square root of n. So therefore it would be 16 divided by the square root of 6. And it's going to be 6.532 days. And I believe they want us to interpret. So what does that mean? That means if we take many samples of size 6, and that's important, right? Because what we just did was we made it a condition. So yes, it met the 10% condition, but we made it a condition. This calculation is based on the square root of n, which was the square root of 6. So the only statement that we can make here is based on a sample of size 6. So if you take many samples of size 6, we expect the sample mean to typically vary from 266 days, the population mean, by 6.532 days. So think about this woman up here. She is a single sample, a single person, sample of size 1. Let's put it like this. She might be single. So a sample of size 1. And so she's not actually considered in this example here because we have to have a based on a sample of 6. So find the probability that the mean pregnancy length for the women in the sample exceeds 270 days. So in the sample, we're looking at, this is still under the umbrella of our 6 pregnant women example. And so what we're going to do is we're going to draw in our normal distribution. We are looking at this 266 here, and based on our problem parameters, we've got 270 days, so we want to know this part here. And what we're actually considering, and this is why this is important here, because we're not actually considering the same numbers in here, right? We're considering the 266. But our standard deviation is that 6.532, right? And so that's one of the important distinctions to draw when we're talking about a sampling distribution, is what is the sample size, because that's going to affect our sample distribution standard deviation here. And so in this case, our z-score is going to be equal to 270 minus 266 over 6.532 to give us a z-score of 0.612, which is going to lead us to 27.03%. And I want you to think about this for a second, right? So what we just did here is we affected the standard deviation, but the cool part about the sampling distribution for means is it's still approximately normal. So even though up top we were calculating the same thing, right? And we did a max of 270, or sorry, a min of 270, a max of 1,000, and then we did a mean of 266 and a standard deviation of 16. Down here, because we're talking about this specific sample size, our calculator is going to look like this. We're going to do normal CDF, and we're going from 270 to 1,000. But we still have 266, but now we have 6.532, and this is min, max, this is our mean, and this is our standard deviation. So we put like this, right? And so of sample size 6, we have this, and when we put that into our calculator, we actually do get that 27, so 0.2703 on the calculator. Okay, guys, so keep in mind, we talked about proportion the other day. Now we're talking about the mean of a sampling distribution. Keep in mind the purpose of those, right? So that sample proportion is used for a categorical variable. This is used from that quantitative variable where they give you some numbers you can actually find the mean of, and keep in mind that sample size. All right, thanks for watching, guys, and we'll see you next time. Welcome back, guys. Today we're going to talk about the central limit theorem. This one's huge. So anytime we're doing any sort of sampling, sample size is a concern, and this is one of the things that is going to help us figure out, do we have a large enough sample size, and what can we say about a population from a sample? So the central limit theorem kind of helps us out with that, because it gives us parameters for, how do we determine sample size, and it's actually really pretty simple, pretty straightforward. So here's the central limit theorem. Central limit theorem. Okay, central limit theorem says this. The sampling distribution of x bar will be approximately normal if, when the sample size is large. right? And n is greater than 30. So if we have samples of greater than 30, then our sampling distribution of x is going to be approximately normal, not our data. The sampling distribution of x bar, so the sampling distribution of the means important will be approximately normal. So what does that mean? Basically, that helps us do this. If the distribution is normal, so it is approximately normal, we can find a z-score. Which is going to help us do what? It's going to help us assess how close is it to the mean. It's going to help us assess how well do we do it compared to others, things like that. So our z-score is going to look like this. Z is equal to x bar minus r mean over r standard deviation divided by the square root of n. So this is based on the fact that, we had from our previous lesson that our standard deviation was the standard deviation of the whole thing divided by the square root of n being our sample size. Also important to consider the fact that we have to now keep our sample size consistent if we're comparing them, but we're not going to talk about that just yet. So let's talk about Keith. He's a manager of an auto care center based on service records of 3,500 customers from the past year, the time and hours that a technician requires to complete a standard oil change and inspection follows a right-skewed distribution with the mean of 30 minutes and a standard deviation of 20 minutes. For a promotion, Keith randomly selects 40 current customers and offers them a free oil change and inspection if they redeem the offer during the next month. Keith budgets an average of 35 minutes per customer for a technician to complete the work. Will this be enough? So think about what this means. So they did 3,500 oil changes. That's a lot of oil changes, right? They found that the mean was 30 and the standard deviation was 20 minutes. Think about what that means. So here's 30. It could take up to 50, but it could take 10, right? So Keith is banking on this 35 minutes being enough. So the question is, describe the shape of the sampling distribution of X mean for samples of 40 randomly selected customers. So he has a sample size of 40. And we went with the sampling distribution of X bar, which means he's taking 40 people and he's finding the average. He's finding the average of the amount of time that it takes. Then he's taking another group of 40 and taking the average time that it takes. Then another group of 40. So the sampling distribution for X bar for samples of 40 doesn't mean one sample of 40. It means all possible samples of 40. What is the sampling distribution going to look like? Well, because n is equal to 40, which is greater than 30, greater than or equal to 30. So the sampling distribution of X bar is approximately normal. Okay, because he's taking sets of 40, not one set of 40, all sets of 40, and the sample size is greater than 30, that means that we're going to get this approximately normal situation. So if we want to find the mean and standard deviation of the sampling distribution of X, what's cool is because it's approximately normal, we've got the mean of our sampling distribution is equal to the mean of 30. This is actually a really great comparison tool that we have now. And so our standard deviation of X bar of our sampling distribution is equal to the the standard deviation of our overall data divided by our sample size. Lost my cursor there, sorry. So that's going to be 20 minutes was our standard deviation. We're going to divide by the square root of 40. And what we get is that our new standard deviation is 3.16 minutes. Okay, 3.16 minutes. So for our samples of 40, it's 3.16 minutes. So what we have to ask ourselves is our 10% condition met? Because we want to make sure that if our one sample that we have, our samples that we have, is less than 10% of our population. So is 40 less than 1/10 times 3,500. Indeed it is, because 40 is less than 350, so our 10% condition is met. So what we can do is we can say this works. This is our standard deviation. This is our mean. And so when they ask us the question to calculate the probability that the average time it takes to complete the work exceeds 35 minutes, that's actually the question, right? So Keith thinks he's some kind of genius, and he's like, oh man, I've got this 35-minute threshold here, and I know that the mean is 30, but I'm feeling like, right? But I'm feeling like because the standard deviation was 20, what are we going to do? So he selects 40. So here we go. So our z-score on this is going to be equal to 35 minus 30 over our new standard deviation of 3.16, because that takes into account the 40 sample size. And that's going to be equal to 1.58. When we look that up, we are going to find that that is equivalent on our z-score table of 0.0568, which is, this is, 5% of the time. So maybe Keith is looking like a genius, right? And so what we can do is we can say, we could also do this as a normal CDF, right? Normal CDF. We could say our min is 35. Our max is 1,000. Our mean would be 30 because it matches. And our standard deviation, of note, it's really actually this, right? But what we put in our calculator would be 30, 3.16, and that would be equal to 0.0568. So how can Keith be 99% sure that he doesn't go over budget? Well, what he could do is he could say, I want to be 99% sure, so I could do my inverse normal, right? And I'd say this, 0.99, 30, 3.16 is equal to 37.75 minutes. Okay, so 99% sure he doesn't go over budget. What he would do is he would say 37.75 minutes. So what we did here was 99% of the time, so the probability is 99%, with a mean of 30 and a standard deviation of 3.16, it would be 37.75 minutes. So if he said 38 minutes, he'd be like 99% sure that he doesn't go over the time. Okay? So, that's how the population and the mean go together. The central limit theorem helps us pick out a sample size. It's going to help us figure out how things can be approximate normal using that sampling, that sample distribution. Okay, guys? Thanks for watching, and we'll see you next time.